Observe a gymnast executing a flawless backflip on a balance beam. Now, look at her sitting perfectly still on a bench with her eyes closed. To an outside observer, these two states are absolute opposites. But to the human nervous system, the difference between vivid imagination and physical execution is remarkably thin. This occurs through motor imagery, an active cognitive state where the representation of a specific action is internally reproduced within working memory without any actual motor output. Motor imagery is a measurable neurophysiological event that takes place within the brain's motor pathways, distinct from the abstract concepts of general visualization. High performers, from Olympic swimmers to specialized surgeons and stroke patients in rehabilitation, rely on this mechanism to acquire and refine new physical skills completely offline. This raises a central question. How can a person induce neuroplasticity and improve a physical skill solely by thinking about a movement? We are going to map the neural correlates of motor imagery, explore how it drives structural brain changes, and break down the 7-part pedal-up model used to engineer a perfect mental repetition. The visual processing network in the human brain operates in a hierarchy. When you see an object in the real world, you rely on bottom-up sensory perception. When you imagine an object, you rely on top-down generated signals. There is a strict biological difference between visual imagery, or watching yourself in the third person, and kinesthetic motor imagery, feeling the physical sensations of a movement in the first person. The ideomotor principle states that vividly imagining an action activates the exact same neuromuscular pathways as physical execution. In neuroscience, this overlap is called functional equivalence. Mental rehearsal and physical execution share a nearly identical neural architecture. Brain imaging reveals that motor imagery specifically activates motor control regions, the primary motor cortex, the supplementary motor area, and the premotor cortex. The primary motor cortex, or M1, is the region directly responsible for executing systematic, somatotopically organized physical movements. The supplementary motor area and premotor cortex work in sequence with the M1 to plan the motor program internally, preparing the body to move without sending the final electrical trigger to the muscles. During this internal simulation, the neuromuscular activation mirrors the pattern of physical execution, merely reduced in magnitude to prevent actual movement. Motor imagery acts as a live rehearsal of a biological motor sequence, engaging the brain's executive machinery. If motor imagery is a true physical simulation, it should trigger the body's unconscious autonomic systems. Neuroscientist Jean Desetti tested this by measuring the precise time it takes subjects to physically walk to a target versus mentally walking to that same target. In the baseline condition, the time it took subjects to mentally walk the distance was identical to the time it took to physically walk it. Then, Desetti asked the subjects to imagine walking the exact same distance while carrying a heavy 25-kilogram weight. This visualization compares the two mental walks. When the subjects imagined the 25-kilogram weight, their mental walking time increased by 30% to account for the imagined physical force. As this line graph shows, during the heavy mental walk, the subject's actual heart rates and respiration spiked precisely when the mental weight was introduced. The autonomic nervous system actively prepares the body for metabolic exertion during motor imagery. The brain runs a physical simulation that the body treats as real. These immediate autonomic responses eventually compound into long-term structural brain changes. Repeated motor imagery strengthens synapses within the basal ganglia and corticocerebellar networks, regions involved in the direct coordination of movement. This neural strengthening results in sharper coordination between agonist and antagonist muscle groups, leading to skill acquisition without physical exertion. A study by Smith and colleagues quantified this impact by testing expert golfers on a complex movement, the bunker shot. This chart illustrates performance improvements across 4 groups: a control, a physical practice group, a mental practice group, and a combined practice group. The motor imagery-only group showed a significant performance improvement compared to the control group, despite never taking a single physical swing during the trial. The group that combined physical practice with motor imagery yielded the highest statistical improvement overall, outperforming all other practice modalities. These structural gains depend on an individual's imagery ability, specifically their capacity to control the image and generate a vivid, multisensory experience. Motor imagery physically rewires the brain, functioning as a primary physiological training modality independent of physical movement. Since functional equivalence drives neuroplasticity, a practitioner needs a way to ensure their mental simulation mirrors reality. The PEDALEP model is a 7-part checklist designed to optimize motor imagery and ensure functional equivalence. To see how it works, imagine a softball batter waiting in the on-deck circle before a critical at-bat. The first parameter is physical. The batter should physically engage with the imagery, wearing the actual uniform or gripping the bat while running the simulation. Second is environment. The batter must mentally reconstruct the exact arena, the fans, the weather, to mirror the real-world spatial context. Third is task. The imagined cognitive and physical demands must match the actual task, such as anticipating the release point of a specific pitcher's motion. Fourth is timing. The simulation must occur in real time, preserving the precise temporal accuracy of the motor program. Fifth is learning. The imagery must be continuously updated to match the athlete's evolving skill level. Sixth is emotion. The batter needs to deliberately induce the autonomic arousal expected during the event, such as performance anxiety or excitement. Finally, perspective. The athlete should alternate between an internal feel of the swing and an external visual analysis of their mechanics. PEDALEP acts as a manual for encoding a mental representation directly into the central nervous system. The ultimate stress test for any motor schema is extreme environmental pressure or complete sensory failure. During the 200-meter butterfly final at the 2008 Beijing Olympics, Michael Phelps' goggles completely filled with water right as he dove into the pool. He maintained absolute composure. Blunted to the walls and his competitors, he relied on his internal motor schema and counted his strokes to the finish. He won the Olympic gold and set a new world record while swimming completely blind. He attributed this success to his motor imagery protocol, where he routinely practiced negative outcome visualization, imagining equipment malfunctions to pre-program his nervous system's response to catastrophe. Motor imagery is a localized, targeted stimulation of the brain's motor networks that hardwires execution before the physical event begins. The physical body executes the motor maps the brain has already constructed. Motor imagery encodes these maps before the athlete ever steps into the arena.